はい、OK。
OK。じゃあ始めましょうか。
はい。
はい。OK, hello everyone. Hello everyone. So, this is the second time for me to introduce about free RTK software. And my name is Nobuaki Kubo at Tokyo University of Marine Science Technology. Today, so I am going to introduce the continuously RTKLIB, introduction of RTKLIB and data processing using RTKLIB, and some other past important questions from the many Asian countries. So we have discussed with the researchers at the other countries, and there are many past important questions regarding RTKLIBs, and I am going to introduce these questions and answers. Okay. By the way, so maybe you have a question. How can we set up RTK by yourselves? So that's 2 points. The firstly, if you can use commercial collection services like virtual reference stations or via satellites, PPP, Trimble RTX, QGSS, Madoka PPP, you don't have to set up. All you need is to prepare rover receiver and maybe software. And usually receiver, survey grade receiver includes RTK engine, or u-blox M8P includes RTK engine. And secondly, if you need to set up base station by themselves, you can use RTKLIB, or if you can prepare N-trip caster, it is easy for you to conduct. And if you have any questions, if you have any helps, please contact Dr. Dinesh or me. So this is just, RTK, general RTK method. So you need reference base stations, and you will have rover receivers. You have to set up a communication link. So communication link there are 2 ways. The first one is radio link, real radio link, and the second one is the internet. So 2 main methods, 2 main ways to communicate the collection data from base station to rover stations. And of course, there are 2 ways for RTK, usually real time. So you have to set up communication link, as I said, or post-processing. So you will obtain the observation and navigation data in both base station and rover stations, and you can use RTKLIB for the RTK processing. Or commercial company provides RTK post-processing software, but it's very expensive. Okay, so this is the second test. Second test using 2 receivers. 2 receivers were set simultaneously. So the one is NetR9 receiver. This is a survey receiver. The second one is u-blox M8P with patch antenna. It's very small antenna, 2 centimeter, very small patch antenna and a Trimble antenna. So for the equal comparison, same settings were applied, and GPS plus Beidou plus instantaneous mode. So I am going to introduce what is the difference between instantaneous, continuous, and fix and hold later. Okay. So this is the setting in the case of M8P and the kinematic and the single frequency and 15 degrees, and the other settings same, only GPS plus Beidou, and the integer ambiguity resolution method instantaneous. And okay, so you can refer to these settings after this webinar. So here is the u-blox M8P results between baseline length is only 10 meters. Base station is NetR9, rover station M8P and NetR9. And this is the result of the u-blox M8P. You can see horizontal EW and NS and UD it seems to be very good. I'm sorry, baseline is only not, not 10 meters. It's very within 1 meters. So the performance of M8P is not so bad. It's quite good, but I can say in my personal test results, based on the many test results, M8P is better than M8T in u-blox. Probably the PLL of M8P is more robust and precise than M8T. Okay. So the fixed rate is 99.1% and with for 1 hour and 3,569 results and no long fix. Yeah, no. There are 1, 2, 3, 4, 5, 6, 7, maybe 7 results are long fixes. Okay. And the other than is, just no fixed solutions. And the green color shows the fixed solutions. Okay. So this is the net2R9 RTK results. Of course, 100% fixed rate and no long fixes. Probably the accuracy is several meters in horizontal. Also, even in altitude, maybe several meters standard deviations. So this is these results are the difference between the very low-cost receiver and survey-grade receivers. There is still the difference, even in the open sky conditions. So I would like you to remember that. But, however, so here we set instantaneous, okay, instantaneous. So instantaneous mode, you can see, you will know a kind of real performance of receivers because instantaneous mode uses only single epoch, not multiple epochs, not using. Multiple epochs are not used. So only single epoch data is used in the case of instantaneous, which means in the ambiguity resolutions, you can use RTKLIB use only should range measurement in a single epoch, which means differential GNSS level. Float solutions is differential GNSS level. Float solution is not the level of the decimeter level. It's always maybe 1 meter or maybe 80 or 70 centimeters, okay? So that's why there is a difference between M8P and N2R9 because the differential GNSS, single epoch differential GNSS performance in Net2R9 is better than M8P. Okay, if you have a time, I would like you to check using the same data as I already sent, as I already uploaded in the website. Okay, so the previous one is post-processing mode, and of course, real-time RTK9, real-time mode you can conduct, you can test, so which is called RTKNAV. You just double-click RTKNAV. So I am going to show you the u-blox M8P RTKNAV. RTK was varied using N-trip of base station via the same antenna under perfect conditions. So GQR was also varied, but GLONASS ambiguity resolution is set off. So please remember that if you use RTKLIB with u-blox, if you use GQR, so please GLONASS ambiguity resolution is set off. Okay. Please check them by yourself after you go back to okay, yes. So here is the configurations, how to do the RTK. So in my case, in our laboratory case, so base station is Net2R9, and we can use N-trip server, N-trip caster from these base stations. And the rover side is on, we prepare u-blox, and maybe this is Skytrack, low-cost RTK, single frequency RTK receiver. And u-center maybe we can use, or RTKLIB you can use. So collection data is received via internet. GNSS raw data is received via USB serial. So USB serial and internet. So you have to connect the internet, even in the laptop PC. A laptop or a pad or a Raspberry Pi. Yeah? So here is the important settings in RTK Navi. So RTK Navi input streams. So I'm sorry. So input stream. So RTK Navi input stream here. This is input stream and input stream. So in my case, Rover we use serial and the format of course u-blox. And the base station is we use network 9, so that's why N-trip client we set, and we set up IP address and password for network 9, and the format is RTCM3, so for multi-GNSS. And the options, setting 1, kinematic, single frequency, mask angle, broad, yeah, blah, 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 GPS, QGS, Beidou, and okay. And setting 2, we set continuous and on. Here is GPS, Beidou, QGS. GPS, QGS is, same. No. We can use QGSS same as GPS. So that's why we can use both satellite in the ambiguity resolutions, but the Beidou, so you have to check on or off. On means we will analyze Beidou ambiguity resolutions, okay? On. But however, as I said, if you set GQR and it doesn't fix, please try it's again off, off or on. Minimum ratio test, minimal ratio to fix ambiguity, we set 3 and positions. So please remember that you have to set up the precise base station position. So blah, 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 blah. So this latitude, longitude, and height, these are the precise positions in our base stations. And you have to set up by yourselves. Of course, if you actually, you don't need the very precise positions. Maybe 1 meter, 2 meter deviations is okay. But of course, the lower positions will be deviated based on your errors of the base stations. So here is the just results of real-time results. So RTK Navi version 243 B28 or RTKPLOT, so real-time solutions, and it's very good. It's 100% RTK. No, 100%, sorry, differential GPS, sorry, differential GPS. Differential GPS. なんでだ? Oh, I'm so sorry. I will prepare the RTK result in this slide, in addition slide, if I upload this file. I'm so sorry. So here is also the very many years ago we tested RTK Navi using the a little bit better antenna, Novatel antenna. Novatel antenna and Novatel receivers. So this is fixed compared with single point positioning. So 3 or 4 meters deviation you can see. Of course, RTK is much more accurate. So here is our campus. It's a small yard. So we have to consider the limitations of RTK. So normally the coverage of RTK is 10 to 20 kilometers. Now in Japan, 20 kilometers is so-so, maybe okay, even in the single frequency u-blox receiver. It strongly depends on the ionospheric activity and also tropospheric wet term. But the recent commercial RTK engine like Trimblue, Topcon, and Septentrion, Novatel can cover up to 50 to 100 kilometers. But this is just our test results, so please check it by yourselves. Also, you can use wireless FKP collection services. This is Japanese collection service in Japan. The commercial company produces real-time collection data through the N-trip using several base stations. QGIS also provides similar collection data through the L6 signal. I'm sorry, inside Japan. It is challenging because the message bit rate is 2 kbps, so which is called the centimeter level augmentation system, CLAS. So we have tested many times until now. So you will see the test results in the near future. PPP, precise point positioning, does not have limitation in the cover areas. So it provides precise orbit and clock of GNSS. Maybe commercial service also provides ionospheric term. So it means that you have to remove ionospheric, tropospheric errors as much as possible based on your lower receivers. It takes 5 to 30 minutes and depends on the ionosphere model you have. So if you have a good ionosphere model like Trimblue, so you can converge 5 minutes even if you use GPS GLONASS. And usually RTKLIB, it takes about 20-30 minutes to converge level within 10 centimeter level. So as you might know, QGIS is going to test PPP collection data. So you actually now you can use L6 signal Madoka PPP. So let's move on to the car data and the field test. So car data is post-processed using RTKLIB. And okay, I skip homework and RTK field test. So let's see the car test data. So data was obtained in last year, July 19th, about 30 minutes. So total 100,000 epochs in 5 Hertz. So near our university campus, it's actually the environment is normal urban areas, not dense urban areas. So normal urban areas. So u-blox MAT and a trim net R9 for both lower and reference stations. If you'd like to test by yourself, I already uploaded these data. So let's compare these two receivers. And also we would like to, we want to see the difference between single frequency and dual frequency. And finally, so what is the best setting? Okay, so firstly, we will test MA2P observation data. So here is RTK post 2.4.2. So you can set the time start and time end and the interval 0.2 second. Lower.obs is MA2P observation data. Left.obs is net R9 reference data, and here is navigation data. Let's look at the options. Setting 1, kinematic L1 and 15 degrees. GPS Galileo QGS Beidou, but actually Galileo cannot be used in MA2P because MA2P produces GPS QGS only Beidou, 3 satellites. So setting 2, we set instantaneous. Ratio test minimum ratio is 3. And position is same. Base stations. So like that. So here is the test results of the MA2P. So here is our campus. We start here and course is like that. Like that. Repeat it to this area and go to here and back. Like that. Like that, and back to our campus. So if you'd like to see only RTK fixed positions, you will change from all to quality is equal 1. So quality is equal 1 is RTK fixed solutions. So in total, 5,682 and 2,800 fixed positions we obtained. So 49% in the case of MA2P, u-blox MA2P observation data. But please remember that number is 5,600 is not the total epochs, not the total epochs, because here is actually no solutions. So if you include these all epochs, maybe 9,900 is the real total number. So here is n equal 5,682, which means carrier phase more than 4 satellites are obtained. So in normal urban, even in the normal urban areas, so carrier phase tracking is still difficult, as you might know. So that's please be careful. The number is 5,600. It's not total epochs. Okay. So, but if you set, so this is just a one example to improve RTK. If you set minimum carrier to noise ratio here, SNR mask setting 1. So we didn't set up in the previous mode, but here is 35 in every elevation angles on 35 minimum decibel hertz we set. As a result, so you can see the fixed positions was improved so much. About 2,000 epochs was improved. And also, number is 9,500. So what does it mean? From 6,000 to 9,500. Because by setting the SNR mask minimum carrier to noise ratio, so RTKLIB does not reject the solutions based on the chi-square test. Chi-square test. Please remember that. RTKLIB always includes chi-square test in the least square method residual. Okay, so this is very important. There are many questions about these issues. In the urban area, in dense urban areas, RTKLIB availability is so bad because the least square method in shield range based large residual RTKLIB does not provide the solutions. Of course, no RTK. Okay, please remember that. Please remember. Once you set only this minimum carrier to noise ratio, the total number was increased and RTK result fixed solutions was also improved so much. Okay. So next is if you remove QGS, so we just wanted to see the performance of QGSS in GPS plus Beidou plus in addition QGS. So that's why we remove QGS from the satellite from these solutions. So 500 epochs was reduced because at that time during this period QGS was 80 degrees in elevation. So that's why even in one satellite there is a much how can I say contributions in this kind of RTK. Normal urban area. Okay, next is Netto R9. Netto R9. I just change from u-blox to Netto R9 here, observation data, and the other settings is totally same. Interval also 0.2, and actually 6,800 epochs was the fixed solution. So that is that is the real difference between single frequency, low-cost single frequency receiver and survey-grade receivers. The main reasons, the main reason is due to the accuracy of the shield range, I guessed. So this is my personal opinion, but probably it's correct. The accuracy of the shield range is totally different from between u-blox and Netto R9. Okay, so 2,000 epochs is different. But of course, the settings is same. Setting is same. And if we switch from single frequency to dual frequency in the case of Netto R9, because Netto R9 produces dual or triple frequency observation data. So we can change from L1 to L1 plus 2. So what happens? So 1,600, 1,700 epochs was improved by the changing from single frequency to dual frequencies. And 87% of fixed solutions, even in the normal urban areas. So here, actually, normal urban area, but here, this intersection, and this area is actually dense urban areas. Okay, so next is the comparing two post files. So I have had similar questions in the previous webinar. So you can compare two post files. So left one shows the previous this test results, only Q equal 1. So only fixed solutions. And the right figure shows the post-LVX result. So post-process, RTK, FOG, and speed sensors. So it's actually very good. Always within 10 centimeters accuracy they have. So post-LVX 2, plot 2, and previous real test results, plot 1. And if you click 1 minus 2, you can, what happens if you click -2? You can see the difference in the same GPS time, and you can compare the test results between two figures. So this is very convenient. So it seems to be that this is 10 centimeters. It seems to me that most of test results comparison within 10 centimeters. Probably these results are fixed solutions and the correct fixed solutions. But these one, 40 centimeter and 1 meter, this one is the long fixes. But the long fixes only several epochs if you use the network line. So only several epochs, even in the normal urban areas. If you use network survey grid receiver and RTKLIB, the long fixes is quite huge. So homework I will skip, but if you have time, please try to find the best settings of RTKLIB using the u-blox data, both reference and level stations. And the best means the highest number of fixed solutions within 30 centimeters based on post-LVX file. You can see like that. So 30 centimeters is like that. 30 centimeters is the lane recognition level. And also, simultaneous data is required. So in RTK or differential GNSS, probably you already know. So you need to prepare the raw data at the base station to include your period at the lower stations. I guess you already know this one. Skip this one. And I didn't talk about PPP in this webinar, so I'm going to introduce briefly about the PPP. So PPP, the feature is you only need a single receiver, no relevant stations, and efficient analysis for many receivers. Efficient analysis means the PPP engine is included in many receivers. And the precise estimates you need, and the conventionally post-processing. The applications, GPS seismometer and meteorology and precise orbital determination for LEO, precise time transfers. Okay. So here is the two best good examples in kinematic PPP and static PPP. So Mr. Takasu introduced these two examples. So for example, in Chile, I guess there was a very big earthquake, magnitude of 8.6. It was quite large. And actually, Takasu-san got raw data from IGS-CONZ in Chile country, and he realized that even in the RTKLIB, we can see the very large deformations using kinematic PPP because we cannot use RTK. So we have no idea about the base stations in Chile. But in the case of PPP, all we need is just observation data, one observation data. So fortunately, there is IGS stations in Chile. And the static PPP station GeoNet 087A37, this is in Japan. So interval 1 day and 1 day, 1 year. So you can see this kind of deformations, maybe centimeter level. So, but it's quite accurate because 24 hours, average 24 hours is quite accurate even in PPP. Maybe millimeter level. Maybe millimeter level. But height solutions is not so good. Okay, so maybe someone would like to use PPP using RTKLIB. So I will show you how to use RTKLIB in the case of PPP. So I used 24 hours raw data, 15-second interval. You already have. This is the test data already uploaded. if you need a centimeter level, you should use a dual frequency receiver. So that's why I chose network 9 data. So you can download other files required in PPP as follows. So precise FMS, precise clock, CCDIS, NASA, satellite antenna information, and text, and the ERP file. Also, it's same FTP site. So if you need additional files, please check by yourself. So I actually use these 4 files. So RTK post version 243, patch 26. And here is, you already have the network 9 observation data at our base stations. And the navigation data is required, FMS data, and precise FMS and the precise clock. And the setting 1, PPP static, dual frequency, mask angle 15 degrees, and the GPS GLONASS QGS we set. Because RTKLIB might not work Beidou or Galileo. I am not sure. Yeah, I will check later. So the files is important. So you have to set up at least satellite antenna PCB file. So I use IGS 142,000.ATX. So this is updated maybe last month. Okay. So ERP is also set in here, EOP data file. Let's see the results. So actually you can do the similar test because you already have data and you can download from this website, these websites. So here is the PPP static results, real results. So 0, 0, 0. These longitude, latitude, and altitude 0, 0, 0 are the RTK fixed solutions based on F3 solutions in GeoNet, in Authority of the Geographical Survey Institute in Japan. So it seems to be PPP results converged into this F3 solutions is quite good. And yeah, so if you set a PPP static, maybe millimeter level, but a little bit, there is maybe 2 centimeter deviations. In latitude is 0, and the longitude is maybe a little bit 10 centimeter deviations. And the right figure shows the first 1 hour result here. So within 10 centimeters in terms of horizontal, maybe at least 15 to 20 minutes it's required. So latitude is quite good, but longitude is 20 minutes is required. And height is also 15 and 20 minutes. But later, it's a little bit more deviated. Okay, so let's go to the past important question that I already talked. So multi-GNSS RTK is nowadays is very popular. So most of receivers includes RTK engine, and these RTK engine uses multi-GNSS, GPS, QGS, Beidou, GLONASS, and of course Galileo. So this is for satellite case. So please remember that in RTKLIB and most of RTK engine, we cannot use GPS, QGS same as Beidou. So which means you have to set up the 1 primary satellite in each navigation satellite. Russian, GLONASS, and Chinese, Beidou, and GPS, QGSS. So that's why GPS, QGS for satellites, Beidou 3 satellites, GLONASS 2 satellites, in total 9 satellites we have, but ambiguities, in terms of ambiguities, so 1 primary satellite and 3 secondary satellites, so double difference, 3 double difference, and Beidou 2 double difference, and GLONASS 1 double difference, which means 1, 2, 6, 3. 3 plus 2 plus 1. Only 6 ambiguities have to be resolved in these cases, we actually have 9 satellites, but 6 ambiguities will be resolved. So it is same as RTK, and also other RTK engine probably same, because the frequency is different. So single L1CA is the same 1575, and Galileo maybe we can use in similar way, but base is 1561 is different. So that's why it is quite difficult to use GPS QGIS including Beidou. And the required satellite number for reliable RTK. Reliable RTK means, about approximately 99% of correct fixed ambiguities. 91% is maybe long fixes. So as I already said, we have to discuss the number of ambiguities, not number of total satellites, number of ambiguities, because the number of ambiguities is quite important in lambda method. Lambda method strongly depends on the number of ambiguities. So with more satellite, the reliability and the fixed rate of ambiguity resolution increases. This is true. Please remember that. And I just just show the this table. So this is my personal opinion. This is not general opinions. So if you use dual frequency, open sky, maybe 5 satellite is okay. And urban area, even in dual frequency sub-regular receivers, maybe 10 satellite is required to obtain 99% reliable RTK. On the other hand, single frequency, of course, single frequency is 1/2 of the ambiguities, approximately. Open sky 10 satellite and urban area 20 satellite is required. But you know, there is a contradictions because the number of usable satellites, which means number of ambiguities in urban areas, is sure to decrease compared with open sky areas. So there is a contradiction, unfortunately. So open sky conditions, we usually have GPS, QGIS, Beidou, maybe in Asian countries, more than 20, 25. So 5 should be okay. But urban area is 10, is maybe 80% or 70%. So there is a contradictions. Okay, so I have had maybe several questions in last year, even this year. So why is the availability of dense urban areas so bad in RTKLIB? So I already talked. So here is the same observation data we used in single point positioning. So left figure, so only 4,200 epochs. And right figure shows the 11,500. Why is availability so different? Even in the same data, GPS, QGIS, Beidou in 2016 we obtained. Here is actually, Tokyo stations, and it's very dense urban areas, so business areas. So what is the difference between two results? Do you know? So I just change the minimum carrier to noise ratio. The left one is no minimum carrier to noise ratio. Right one is minimum carrier to noise ratio. I set only 35 decibel hertz. So if you set 35 decibel hertz, the number of solutions, least square method, is increased from 4,200 and 11,000. Please remember that. In RTK uses chi-square test. Chi-square test, this is my personal opinion. Chi-square test is too stricted in this case, too stricted. So please remember that. And what is the best mode in RTK? So I have had many questions. Yeah, in similar questions. What is the best mode in RTK? Option setting 2. Or what do these mean? Okay, continuous, instantaneous, fix and hold. So RTKLIB, so before we explain these differences, RTKLIB is not designed for the purpose of navigation under dense urban areas. So Mr. Takasu-san always talks about that. RTKLIB is not designed for the purpose of navigation and dense urban areas. So although it can be used even in the low data obtained in urban areas. So we know, but RTKLIB is originally for open sky mode. Okay, so answer. Answer is very difficult. Mr. Takasu developed those modes based on his own ideas. I already talked with him. It means that there is no reference papers. Of course, he actually read a lot of papers, but he developed those modes based on his own idea. There is no reference. But technical point of view, lambda plus ratio tests are always used in RTKLIB, so in kinematic. So that's why there is limitations in terms of lambda plus ratio test. So maybe other tests might be better. So each mode has characteristics as shown in these tables. So 3 kinematic mode and explanation. Instantaneous, only single epoch observation data is used to resolve ambiguities. So which means float solutions is differential GNSS. And the continuous mode, so Kalman filter, as you know, Kalman filter is used to converge the float solutions. So it is better than instantaneous. And fix and hold. So basically it's same as continuous because Kalman filter is used. But the one difference, once the reliable correct ambiguities are resolved, those ambiguity information are retained. So which means they don't try the ambiguity resolutions. Once the reliable correct ambiguities are resolved, those ambiguity information are retained. So let's check in detail. So I just show the suitable test environment in 3 kinematic modes. So instantaneous, the accuracy of flow solutions is like differential because single epoch solutions. So in the case of open sky, instantaneous mode should be okay. So you can see the real performance of your receiver. If you compare the receiver performance, maybe it is better for you to use instantaneous mode. The accuracy of code phase is not so good. You cannot obtain the better RTK results. You will know if you use instantaneous mode, such a kind of the receiver limitation. So in the continuous mode, the accuracy of resolution will be better as time passes because Kalman filter is used. But the most important thing is without cycle slip. Without cycle slips. If you have many overpasses, which means cycle slips, the RTK performance is similar to the instantaneous mode. Okay, please remember that. Open sky semi-urban continuous is always better than instantaneous, but urban areas is maybe similar. Finally, fix and fold. The accuracy of resolutions will be same as continuous. The only difference is reliable correct ambiguities are retained. If these ambiguities, so this is much more important. If these ambiguities, so we thought that reliable correct ambiguities, but this is not 100%. If these ambiguities are not correct, you will see long fixed solutions for several times, maybe for a long time. Please be careful to use fix and fold mode. Open sky and semi-urban hold mode is better than continuous, and of course, it's better than instantaneous. And urban areas, hold continuous, instantaneous, I am not sure. So I would like you to compare these modes by yourselves. These urban areas, maybe instantaneous is slightly better than continuous and hold mode because the Kalman filters overpasses many cycle slips. Kalman filters does not work so well. Kalman filters is always, it is assumed normal distributions. Okay, so you need a reference system to evaluate your own RTK test results. So here is 0 baseline, 0, this is horizontal errors. Sorry, this is Japanese longitude and latitude. Latitude, and zero line is reference system produces this 0 line. Without this kind of reference system, you can't evaluate RTK test results. Okay, because RTK test results always, produce centimeter level. So that's why you have the better reference system. Always produce centimeter level, even in the, dense urban areas. Without this reference system, you can't evaluate RTK test results correctly. And RTK performance is quite different according to the time. Okay, I'm sorry, this is Japanese. In Tokyo, I'm not sure when, maybe 2016, 2017 in some day. So 24 hours GPS time and the number of usable satellite, GPS, probably GPS, QGS, Beidou, and the mask angle 15 degrees, more than 20 satellite, it is okay. But mask angle 30 degrees, 45 degrees, which is similar to the environment of urban areas, it's like that. Here is, more than 10 satellite. Maybe if you use survey grade receivers, it's okay. But even if you use survey grade receivers, here, this time, maybe RTK is not so good. Okay? RTK performance differs with the time. And you can expect, you can predict by using almanac information or whatever. So 10 minutes left, and Didn't sensei,